Welcome to this video on dynamics, where we calculate the force required to push a block up a ramp with friction at constant velocity. How much force is required to push a 12 kilogram block up the ramp shown at constant velocity if the coefficient of friction between the block and the ramp is 0.2? We start this question by adding our forces to our diagram. Our force of gravity acts straight down on the block, and we call this Fg. We break Fg into its perpendicular, Fg perpendicular, and parallel components. We call this Fg parallel. The component Fg parallel is the component that's responsible for bringing the block down the ramp. If we were to just let this block go on the ramp, this would be the component of gravity that would cause it to go down the ramp and accelerate if it overcame the force of friction. The component of gravity Fg perpendicular is what keeps the block on the ramp. Now, technically right now it's sinking through the ramp because these forces are unbalanced, but opposite Fg perpendicular, we have the force Fn, the force normal, which is equal in magnitude and opposite in direction to Fg perpendicular. So our block is neither floating away nor sinking through the ramp. The forces in the perpendicular direction are perfectly balanced. In this question, the block is being pushed up the ramp, so the force of friction acting against this acts down the ramp against the force applied up the ramp. So our force of friction is backwards and parallel to the ramp, down the ramp, and this is opposite our force applied, which is parallel to the ramp and up the ramp. We've now got all our forces. Our Fg perpendicular is equal in magnitude and opposite in direction to our Fn. Pushing our block up the ramp is our force applied, and opposing this force up the ramp is our force of friction down the ramp, and our component of gravity, Fg parallel, also down the ramp. Geometry can be tough for a lot of people, and we need this angle right here if we're going to solve for the components of this triangle, but we can easily find it by manipulating a few 90-degree angles. So imagine this Fg here continued here, creating this triangle here. This would be a 90-degree triangle. So if this is 60, that would mean this angle here would have to be 30 degrees. Now, we drew this line here, Fg perpendicular to the surface, which means this here again is a 90-degree angle. That means this angle right here also has to be 60 degrees because these two angles have to add to 90. We solved this question using our standard equation for force. Force net is equal to ma. So let's start by writing this at the top. Force net is equal to the mass times the acceleration. We break our force net into the forces that we call our winners, and we subtract from these the forces that we call our losers. And this is equal to the mass multiplied by the acceleration. Now this question is a little unique because it's happening at constant velocity. So that means we have no acceleration. Our acceleration is equal to 0, causing this right-hand term to go to 0. And normally I say our winners are our forces that are in the same direction as the acceleration. Now, when we have no acceleration, we just need to choose a direction that we're going to call our winner and a direction that we're going to call our loser. So let's call up the ramp our winning forces and down the ramp our losing forces. So acting up the ramp, we have our forces that we're going to call positive, and this is our force applied, or our winner. And acting down the ramp, we have our force of friction. So we subtract our force of friction because we're calling the forces that go down the ramp our losers. And we also have our component of gravity Fg parallel that is bringing the block down the ramp and acting against the force applied. So Fg parallel. And this is equal to 0. Because this equation is equal to 0, we can rewrite it conveniently with all positive terms because we can add the force of friction and we can add the component of gravity parallel to the other side. And this leaves us with force applied is equal to force of friction plus Fg parallel. So all we've done is moved these two negative terms to the other side so that we only have positive terms. Let's now expand these terms individually into things we can calculate. So our force of friction, as shown on our formula sheet, is equal to mu Fn, the coefficient of friction, multiplied by the force normal. Now Fn, as shown up here, is equal in magnitude and opposite in direction to Fg perpendicular. So this term can again be rewritten as mu Fg perpendicular. Next, we need to find our components of gravity. So we'll start with Fg perpendicular. Fg perpendicular is this side right here. It's the adjacent side. So we'll use cosine to find Fg perpendicular. So cosine of the angle is equal to the adjacent side divided by the hypotenuse. Substituting the values from our triangle, we have cosine of 60 degrees is equal to Fg perpendicular divided by Fg. To get our term of Fg perpendicular all alone, so we can substitute into here, we multiply both sides by Fg. On this side, we have Fg divided by Fg, which is equal to 1, and we're left with our term Fg perpendicular. And on this side, we're left with cosine of 60 multiplied by the force of gravity, Fg. And now we can substitute what we found here into here for Fg perpendicular so that we have only values that we actually have numerical numbers for. So this becomes mu multiplied by cosine of 60 multiplied by Fg, the force of gravity. Now similarly, we need to find the component of gravity Fg parallel. Fg parallel is the opposite side, so we'll use sine of the angle is equal to the opposite side divided by the hypotenuse. Substituting the variables from our triangle, this gives us sine of 60 degrees is equal to Fg parallel divided by Fg. And again, because our Fg parallel is being divided by Fg, we multiply both sides by Fg to get our term for Fg parallel all alone, because Fg over Fg is equal to 1, and on this side we're left with sine of 60 multiplied by our force of gravity Fg. And we can now replace this component with variables that we have numerical values for. So Fg parallel is equal to sine of 60 multiplied by Fg. Rewriting this equation with all our new terms, we get force applied is equal to mu cosine of 60 Fg plus sine of 60 Fg. Let's bring this equation to the top so that we can do our final calculations. Before bringing in values, we just need to make one more simple substitution of an equation into what we've built here, and that's Fg is equal to our mass multiplied by our gravity. So rewriting this equation with our substitution for Fg, we get force applied is equal to mu cosine of 60 multiplied by the mass multiplied by gravity plus sine of 60 multiplied by the mass multiplied by the value of gravity. Substituting numbers, this gives us force applied is equal to 0.200 multiplied by cosine of 60 multiplied by the mass, which is 12 kilograms, multiplied by the value of gravity, 9.81 meters per second squared. All of this added to sine of 60 multiplied by the mass, which is again 12 kilograms, multiplied by the value of gravity, 9.81 meters per second squared. Completing this multiplication, we get force applied is equal to 11.772 newtons plus our second term here, which when multiplied gives us 101.949 newtons. And we keep a few extra decimal points to avoid rounding errors. 11.772 plus 101.949 gives us a final answer of a force applied equal to 114 newtons. And this answers our question. How much force is required to push a 12 kilogram block up the ramp shown at constant velocity if the coefficient of friction between the block and the ramp is 0.2? Well, it takes 114 newtons. Thank you for watching this video on dynamics, where we calculated the force applied required to push a block up a ramp at constant velocity against the force of friction.